Kia ora, welcome to the penultimate video in this series on AP Chemistry. Really excited to bring you this one today. It's a very short video, but it's an important video nonetheless, because what we are going to do is we are going to compare thermodynamic favorability, that is the value for delta G, and understand how that directly correlates to the equilibrium constant. So remember, when we talked about delta G, that is Gibbs Free Energy, and we learned how to calculate in that last video by utilizing an equation that delta G equals delta H minus T delta S. Well, we're going to correlate that delta G to the value for K in chemical equilibrium. So hopefully you're excited for this video. I know I am. Make sure you like, comment, and subscribe, and we'll get started today. So we don't have nearly as many student learning objectives because this video is relatively short. I think it's only a handful of slides. But by the end of this video, you should be able to establish a relationship between Gibbs free energy and the value for the equilibrium constant K. Explain which side of a reaction is favored based on Gibbs free energy. Calculate values for K or delta G given one or the other. Recognize that the magnitude of delta G describes how far products or reactants are favored. Describe systems of reactions where an unfavorable reaction is paired with a favorable one to drive a reaction forward. And calculate delta G using Hess's laws concepts. So let's get started. So one thing we need to think about in terms of delta G is that the value for delta G has a direct correlation to the equilibrium constant value K. If delta G is negative, then the forward reaction is spontaneous until equilibrium ends up being reached. Therefore, if delta G is negative, K must be greater than 1, right? Because if delta G is negative, it says that the forward reaction is favored or is spontaneous until equilibrium is reached. Well, if the forward reaction is favored, then K is going to have a value that is greater than 1. And it's vice versa if delta G is positive. If delta G is positive, then the reverse rate of the reaction is spontaneous until equilibrium is reached, and therefore our K value has to be less than 1. When K is equal to 1, delta G is equal to 0. So again, we can directly correlate the value for delta G and understand how that impacts our equilibrium constant. If we think of delta G in terms of whether a forward reaction is spontaneous or a reverse reaction is spontaneous, then we can think about that in terms of the value for K. Now, the equilibrium constant and delta G can be calculated by using the following equation, where the delta G, standard value for delta G, equals negative RT natural log of K. And we can flip that and solve for K if we have delta G by using Euler's number and taking that to the negative delta G over RT. Now, in this case, R is a gas constant, but we're going to be using 8.31. Because it is joules per Kelvin times moles. And obviously when we solve for this, one thing we need to make sure that we keep in mind is that if we're plugging this in and solving for delta G, it is going to be in joules, not kilojoules. So really make sure that you understand that that R value, that unit joule, that's what you're going to get from your delta G. So if it's going to ask you to compare that to a different value, you need to make sure that it is converted into kilojoules. You also look at this triangle here on the right-hand side here, and there's a couple of other calculations that we can do when we're looking at electrochemical potential, but we will talk about those in our next video. So in the Haber process for the manufacturing of ammonia, we're given an equation that we're all probably really familiar with at this point in time. Our delta H is negative 93 kilojoules per mole, and our delta S is negative 198 joules per mole Kelvin. Okay, determine the value for K at 15 degrees Celsius. Well, we can remember from the last equation that we looked at that there is a direct correlation between our Gibbs free energy and our value for our equilibrium constant. The problem is we don't have delta G, so we're going to have to calculate that. And we can utilize that by using the formula that we talked about last time, where delta G equals delta H minus T delta S. Now remember, delta H is in kilojoules per mole, delta S is in joules per mole, so we're going to need to convert delta S into kilojoules per mole by dividing by 1,000. So I'm going to plug all these into that equation, negative 93 minus 288, which is 15 degrees Celsius in Kelvin. And we're going to multiply that by a negative 0.198. And what I get is my delta G value is negative 36 kilojoules per mole. So now I can utilize that value and plug it into the formula that we just looked at in order to solve for K. We have our value for R, which is 8.31. Our temperature in Kelvin, again, is 288 Kelvin. We can algebraically then solve for the natural log of K by plugging all those values in. Now, Again, one thing to keep in mind here is that remember that our R value for this is 8.31 joules per Kelvin times mole. So we need to make sure that our delta G value is in joules as you go through and complete this problem. Multiply through, and then we can solve for the natural log of K. We know that Euler's number to that value is going to give us our K value, which is 3.41 times 10 to the 6th. And if we really reflect and think about it, that makes sense because our delta G is negative. And a negative delta G means that the forward reaction is spontaneous. That equilibrium is going to lie where we have significantly more products than our reactants. So again, making sure that we can correlate our value for delta G with our value for K, really the whole main point of this video. Now, coupled reactions are interesting. So if we have a reaction that is not thermodynamically favorable, that is, it has a positive delta G value, we have to have some external source of energy in order to make the forward reaction take place. So if we have a reaction and the forward reaction has a positive delta G value, it will not be spontaneous. So you have to add energy in order to make that happen. For example, a battery that can be used to drive a reaction like in a remote control, right? Changing the channel from here, it has a positive delta G value. And so you need to add a battery in order to make that happen so that way the reaction is thermodynamically favorable. So in a Hess's law type problem, we can actually combine a non-favorable reaction with one that is favorable to make the entire process favorable. So for example here, the single reaction of glucose and fructose to make sucrose has a positive delta G value. So it is non-spontaneous, it is not thermodynamically favorable, it will not occur. However, if we couple that with the use of ATP in the body, we can get a negative delta G value, and as a result, the reaction becomes thermodynamically favorable through having a negative delta G value. So we can couple reactions that are not thermodynamically favorable with ones that are in order to make the entire reaction thermodynamically favorable. We will do some calculations with this a little bit later on. So hopefully we've met all of the student learning objectives for this video. Remember, we can directly correlate Gibbs free energy with the value for K, and we can calculate delta G using Hess's law concepts by coupling an unfavorable reaction with one that is thermodynamically favorable to make the entire reaction thermodynamically favorable. Hope everybody has a great day. This was the penultimate video. We've got one more to go. It'll be a fairly lengthy one over essentially all of electrochemistry. Hope you have a great day. We will see you soon. Bye-bye.